Good afternoon, everyone. I'm really glad to have the chance to introduce our work named Image Dedusting with Deep Learning-based Closed-Loop Network. I am Xibin and I'm from Robotics and Autonomous Driving Lab, Baidu Research. This is the outlines of this report, including motivations, contributions, details of the proposed approach, experimental results, and conclusion. For the first part, motivations. As we all know, computer vision technologies have gasped more and more attention in construction industry, such as object detection, object segmentation, and 3D reconstruction. However, dust and mist always exist in many industry job sites, which heavily affect the applications of computer vision tasks. Here are two examples of haze and dust. A shows the haze examples and B shows the dust examples. And we can clearly see that heavy haze and dust exist in these images, which can heavily affect the performance of computer vision technologies. So to relieve these problems, in this paper, we propose a closed loop framework, which divides the dusted image into 3 components, including clean image component, atmosphere component, and the transmission component. And in the closed loop framework, a UNet structure with an encoder and 3 decoders is used, which can recover the 3 components simultaneously. And third, to guarantee the network can be well convergent, 2 supervisions are utilized, including clean image supervision and reconstruction supervision. This is the pipeline of our proposed approach from left to right. Given dust or haze image, the network contains an encoder and 3 decoders. And in the encoder, residual group and dense feature fusion module are used to intensify the extracted features. And in the decoder part, in each decoder, the dense feature fusion module and boosted module are used to well recover each component. And with 3 decoders, the atmosphere and clean image and the transmission map can be recovered simultaneously. Next, I want to give more details of each operations in the pipeline. The first one is residual group. Residual structure is often used in deep learning-based frameworks. It aims to intensify the features using a residual mechanism, which contains a convolution, ReLU convolution structure, and an addition operation. It is a commonly used operation that can intensify the extracted features effectively. Second, boosting strategy. This is the equation of the boosting strategy, where G denotes the estimated image after boosting strategy, and G is the dedusting approach. It can be regarded as an enhancement of the input. Thus, better result can be obtained by this operation. Third, dense feature fusion module. DFF aims to sufficiently utilize the spatial information and exploit the features from non-adjacent levels, and intensify the boosted features using an error feedback mechanism. With this operation, the extracted features can be effectively identified. For the loss function, as I described before, we use clean loss and reconstruction loss. For the clean loss, as shown in the pipeline of our approach can recover the atmosphere, clean image, and the transmission map simultaneously. With the recovered clean image, it should be same with the ground truth clean image. So this is the clean loss with L1 loss. And for the reconstruction loss, with the 3 recovered components, the reconstructed input image, input haze or dust image can be recovered, and which should be same with the input haze and dust image. So this is the reconstruction loss, and the final loss is a combination of the 2 losses with the alpha and beta, which is a weight. So the proposed approach can be used for both image dedusting and image dehazing, and PSNR and SSRM are used as evaluation metrics. The PSNR and SSRM are commonly used evaluation metrics in image processing. This is the definition of PSNR, and it is commonly used to quantify reconstruction quality for images and videos. And this is the definition of SSRM, and which is commonly used to quantify structural construction quality for images and videos. So using our approach, we can effectively remove the dust components of dust images. So as shown in the picture, the first row is the input image, and the second row is the results. And test 1 to test 4 are obtained dust-free images. We can see that the dust can be removed by our approach, which proves the effectiveness of the proposed method. For image dehazing, this is another example. The first row is the input haze images, and the second row is the results obtained by our approach, and the third row is the ground truth. And test 1 and to test 4 are 4 examples. We can see that our approach also can remove the haze components in haze images, and clean images can be obtained, which is quite close to the ground truth. Table 1 shows the PSNR results of the 4 images. And in table 1, E1D means approach with 1 encoder and 1 decoder to directly recover the clean image. And we can see that our approach can obtain higher PSNR results, which proves that results obtained by our approach are more close to the ground truth. And the table 2 shows the SSRM results of the 4 images. And we can see that our results can also obtain higher SSRM results, which proves that images obtained by our approach are with better structure information, which can also prove the effectiveness of our approach. So in summary, in this work, we propose a closed-loop framework to remove the dust and haze in construction sites, which divides the dusted image into 3 components, including clean image component, atmosphere component, and the transmission component. And we use a UNet structure to recover the 3 components simultaneously, and to guarantee the network can be well convergent. Clean and reconstruction losses are used. And the image dehazing and dedusting results proves the effectiveness of the proposed approach. Thank you.